Right. But what I was beginning to say is you'll see as we get started the next chapter, and the title is called Sources of Magnetism. It comes from the source of the magnetism comes from moving charges. So one of the phrases we'll have is that magnetism comes from moving charges. So we'll look at currents, and so there'll be times where 28, you kind of have to go through the whole circuitry and figure out what the current is before you can calculate the magnetism, because the magnetism comes from those charges. So I was saying that because in this chapter, you don't really have to worry anything about chapter 28 and how to calculate currents in order to proceed. We're as you are seeing here in chapter 29, is that we just said, if you are given this magnetic field, what does it affect on the world around it? These charged particles that are moving. So that's kind of the first chapter. So we don't really say where did that magnetic field come from, but that's about to change. And then you'll see it tie back to 28. So that was a long way of saying you're fine. You don't need to finish 28 to go to 29. However, in 30, you might run into that challenge because you can't calculate the magnetic field until you know the current, which is what you need 28
for. Okay. Yeah. Thank you. I'll probably switch gears then and go back to 28 and then finish it.
Yeah. So and to be quite honest, maybe even the knowledge of 27 is enough, because 27 was Ohm's law, the simpler circuits, and that's really what they kind of throw at you in 30. You got to calculate the simple circuit to get the current first, then use that to get the magnetism. So they don't usually throw a real complex circuit at you in 30 and make you do a lot of the same work you did in 28, only then to ask you about the magnetic field, but once in a while.
Okay.
No, Tim left us, huh? Come back later. I need to watch last week's. Okay. All right. So I was scrolling down here for something, and I forgot which number you said. So what number?
41 in chapter 29.
Okay, so you're a little ways into here. 41. An experiment is designed to measure the Earth's magnetic field. Oh, using the Hall effect. Okay. Copper bar. Boy, that is poorly photographed or photocopied. Position east-west, current of 8 amps in the conductor, the Hall voltage of what is the magnitude of the Earth's magnetic field. Go ahead and assume N is, okay. Let's see, how do I review this one? Maybe I should go to the textbook for a second and maybe even look at a picture. In fact, I might do it on this laptop so I can grab it and then share that with you, because the textbook had a good picture that probably better than I can draw. Let's see, this would be chapter 29. Okay.
I think I know which picture you're talking about.
Oh, okay. So if that's the case, I probably don't have to redraw the picture here.
It's on page 826, right?
I got 8. Oh yeah, 826. Yeah, perfect. Yeah. That's okay. That's exactly it. And then okay, so I won't bother to redraw it. I'll just maybe I'll write down the results. Delta VH equals IBD over NQ QA is the final result.
Mm-hmm.
But then, and let me go back to the Zoom here. All right, so I won't bother to copy that, but I will turn on the share screen here with the phone and the camera. I just gotta connect Bluetooth here. Okay. So I wrote down the equation. I don't know if that necessarily helps because at this point we could just kind of plug and chug. But here's the idea. Here's that picture they were talking about. If you've got this current going through here, and the one of the important results of the Hall effect was that for the first time in history, we as scientists were able to measure which of the charges are moving, the positives or the negatives. So if the magnetic field is going into the screen, which they do in green, and I actually finally got myself to the store to buy colored pens. I don't know if they show up in color.
They do.
Oh, not too bad. Nice. In fact, I'm kind of curious on a bigger screen. Am I? Oh yeah, I like looks at it. Okay. Anyway, so, but as the negatives move this way, oh excuse me. So if the current's this way, what that means is the electrons are moving this way, and so the force on them, and so force would be this charge, and then V cross B. And so V, and I'm going to use my right hand, is going in this direction. B is into the board, so I'm going to close my hands. So that means V cross B is down. And so the final step is to realize that this part would be down. Now I need to multiply by a negative 1.602. I won't actually do the number, but the negative means then the force would be up. So what's going to happen is electrons are going to be forced upward. And so instead of flowing through the copper piece, I'll give it a little thickness here, they get shoved up to the top. Of course, what that means then is leaving behind, down on the bottom part of this rectangle, would be protons. They're locked in, and I think I said this was copper, if I'm not mistaken here.
Yes.
Okay. And so then what's going to happen is a field is going to build up. Trying to remember author, see if this orange will stand out, but the field, electric field, will kind of build up in this direction. And that, of course, electric field wants to pull the electrons down. So the bottom line is a few electrons go up real easy at first, but then as they start to pile up, they keep other ones from going. So there's an equilibrium established. And so what happens if you took a voltmeter and hooked it on the top and bottom of this copper plate, you would pick up a higher potential here than here. And of course, what it would depend upon, and this kind of maybe is the question at hand here, this is what the author derived, starting with the idea that the magnitude of the magnetic force pushing these up is then equal to the magnitude of the electric field pushing them back down. And so the velocity of these is equal to that. And then they go back to chapter 27, where you have the current is equal to, and there's four terms. Let's see if I can remember. There's the charge, the number, the drift velocity, and the area. I think that's right. Might need to look that one up. Let's see.
IVD, NQA,
Yeah.
NQAV. Yeah, I believe that's it.
Okay. And so that's from chapter 27. And the other thing from chapter 27 is Ohm's law, which then says no, excuse me. I'm going down the wrong road. I don't want to say that. Anyways, I'm not sure where you want me to go exactly with this, but if we put then
Well, I do have one specific question. I think.
Yeah.
So I've worked through most of this. Like you said, it's basically just plug and chug. But I was looking at the solutions because I kind of missed something. I didn't have an A, and in the solutions, it looked like they wrote down magnetic field is equal to NQT times the Hall voltage divided by the current. So I don't know where the A transformed suddenly into a T. It's a lowercase t.
Okay. So I think they did. Before I look up the solution, let me take this and then pull this down. Okay, so Hall voltage. But if you'll see here an N, a Q, and an A. So let me see if this is what they did. I think they just took did they take the N, the Q, and the A? No, and then
The only way I can think about getting a T into this is somehow incorporating like a separation of variables and integrating to get T. But
yeah, I'm sorry. I need to look at the answers here. Because I don't completely understand what you're asking with. I think here. Okay, so chapter 29. Oh, I didn't write down the number. My bad.
that's fine. It's 41.
Should number 41, and let me put it on here. Number 41. And answers to even. So that's not what I want. And solutions is what I want. Okay. All right. So in number 41, you said they did a T.
Mm-hmm. It's a lowercase t.
Yeah, and they just start there, don't they?
Yep. She went into the book and I found page 26 and I worked through the same kind of stuff that you did
Yeah.
to get to the Hall voltage is equal to IVD over NQA. But when I started putting numbers in, it didn't make any sense.
Okay. Okay, so let me move the Hall voltage and then the N, the Q. Oh, okay, wait, maybe I see it here. And the A to the other side. Let me then just go IBD for just a second. In fact, actually, let me just put I and D over here. Okay, so this is not quite where the author starts. He has a B. He has the N and the Q.
Oh, I think I see where it came from.
Then he has the I. Oh, But this,
Is it the thickness? I think he used T to symbolize thickness.
there we go. There we go. It's,
Oh
yeah,
my
yeah.
goodness.
Yeah, both you and I are looking at that T as time. That's thickness. Yeah, because that's area. Yeah. Okay, so because it looks like this, right. The copper piece is like this, and the current is flowing through here. This is the D, and then this is what he's calling the T for the thickness. So area is thickness times D, so that when you put it up here, D and thickness cancel off, and it's thickness. Yep, you saw it. Good.
So clever.
Yeah. You're right. I did the same thing. You asked about that T for time, and I looked at the other. Where did the heck that T come from?
Yeah, I thought it was time.
Okay.
Well, okay, that answers that question. Thank you. I appreciate it.
Sure. Sorry, I didn't see it right away.
No, that's I have not yet seen that. I was not expecting something like that to show up.
Yeah.
I do have more questions. However, I am not the only person in this Zoom session.
Oh,
So I'll
sure.
let somebody else go ahead.
And I'll say again, just like always, if anybody in here, because I know some people are here just kind of waiting for good questions to be asked and just kind of learning as we go along, and other people have questions. So throw it into the chat so I know who is first and
yeah, I think it was me. I didn't throw it into the chat just because no one else was here yet. But
okay.
I got a one question for you.
Yeah.
Let me. Do you want me to share it so you can see the question?
Sure. Because this is from 121.
Yeah, it's from 121.
Yeah, and I need to go back here and give you permission. Let's see. How do I go back to? No, got too many things open. Okay, so let me stop that share. Go to the share option. Oh, maybe you can share. Did I change something?
It says host has disabled attendee screen sharing when I click on it.
Yeah, that's normally what I get. And then there's a little button here. There it is. Okay. Who can share? One participant at a time. I think that's the one. Yeah, good. All right, see if you can share now.
Yep.
Okay.
Cool. So let me see. Where are you? Question I'm looking for. There it is.
All right. So get my piece of paper here going.
Mm-hmm.
And this will be a 121 question. That'll be good. At about 1026. And so it says here a frictionless roller coaster that has a mass. Let me just write that down before I leave the screen here. We got 120 kilograms. It starts from rest. Oh, we got a nice little diagram there. Okay. And so starting from rest means initial velocity is 0. The height is 23.6 meters above the ground. It rolls into a vertical loop that has a radius. And so R equals 6.86 meters, whose lowest point is at the ground. Okay. The normal force on the roller coaster from the track at the highest point is, and so N sub top. Okay, if the roller coaster is released from a lower, so that must be one question. and then we're going to another question here. Okay, so it's a release
Yeah,
from
sort of a two-part question.
okay, yeah, okay. So if it's released from a lower spot, H minimum, it will not have enough speed to make it around the loop. This occurs because the gravitational force is stronger than that is needed to provide the centripetal. This extra gravitational pull pulls the roller coaster off the loop. Now there might be something we need to read in here that is a little different than real roller coasters, but I'll get to that on part 2 here. So let's just have a little talk here. But okay, so I think I got it real good. And the question for the first part is define the normal force, right?
Yeah, the normal force at the top of the loop.
Okay. And this one will actually be, and I can see why it's going to be a little bit of a challenge for you and others, is because this one requires the current chapter you're working on, which is energy chapter, right?
We're on the sort of the conservation of energy right now, but it seems like there's old stuff in there, and that's where I was having trouble sort of marrying the problems together.
Okay, exactly, and that's where I was going with this. That this involves not only the current chapter you're working on, but together with the circular motion stuff you did a couple chapters ago.
Mm-hmm.
All right, so this is what I kind of scratched real quick when I was reading it, and this maybe I'll just put here roller coaster one, so when I label the Zoom videos, I can reference it. But let me do the new stuff first, which actually kind of, but based on what you said, it sounds like that's not your real challenge part. But if I do the conservation of energy, I like to say this, that the energy that you start with is equal to the energy you end with.
So are you solving this part right now? Are you doing the energy stuff and that's going to find you the H min? Is that what you're solving?
No, that's part 2. Let me just focus on the first question, which is define the normal force. And I'm hesitant of which to do first because it is going to involve energy, but it's also going to involve the circular motion stuff.
Okay.
And I'm just choosing to start with the energy one first, just because that's what's new to you.
Mm-hmm.
Okay, so if I did this, if I said the initial place is up here where the roller coaster starts at a height of 23.6 meters with no motion, so no kinetic energy, I would do something like this, mgy initial. And maybe for completeness, I'll just put 1/2 mv initial squared. But I am going to say that initial speed is 0.
Mm-hmm.
Then it comes down, it goes down to the ground, then it goes up, and then I'm going to call final up here at the top of the roller coaster. So there's going to be an mgy final, and there's also going to be a 1/2 mv final squared. And maybe for completeness of your education, I'll put the other form of energy you guys are working with, which is heat energy. So you really have 3 different energies, 4. You're probably working with gravitational potential energy, kinetic energies, heat energy, and then what I call the elastic energy in a spring when you stretch it and compress it. Okay. Now,
so I had a real quick question just generally about this equation versus sort of what Doug showed us, which is he's got, instead of having heat on the right side of the equation, he's got non-conservative work on the left side of the equation.
Oh, okay.
And I just, I've been trying to wrap my brain around it for the last couple of days, and just, you could maybe explain to me the difference there and why one is on the left side and one is on the right side and how that.
Oh, sure. Yeah, absolutely. Okay, so when this equation is being derived, okay, and you'd be a good one to ask. I know that he has shown you guys my lecture videos.
Yeah.
And I don't know if you guys watched them.
Yeah, I've watched both of your lecture videos on both on conservation of energy.
Okay, because it looks like he's also using, or maybe even more using, I'm not sure. I forget the website. It was
I lecture online.
I lecture online. Okay.
So in those, it's more like yours, where he has, in the I lecture online videos, he's got heat on the right side.
Okay.
And then, but in my notes from Doug, I have like on the left side, I've got conservative work plus non-conservative work, or maybe minus non-conservative work equals, potential energy final plus kinetic energy final.
Okay. So, all right. So I'll let me pause on this question for just a moment and answer your general question. This energy equation comes from the idea of work equals the integral of F dot dr. Okay. And then what we do is we say that you could think of F as, and so I'm going to break it into two pieces. On the right-hand side of the equation, I will say and maybe I should say total work, so that this F is actually the sum of a bunch of forces, dot dr. So we could have like the force of gravity, the force from a spring, the force from friction. Okay.
Yeah.
And so I'll just do that for a second. And you can actually say the same thing on the right-hand side of the equation, but instead of calling it the sum of all the forces, you get the net force. Okay. Now I'll start on the right-hand side. If you call this the net force, you could then replace it with MA. You could then replace A with the derivative of velocity. You could then put this dr and dt together and get V, and that's where you get the 1/2 mv squared evaluated from some initial speed to some final speed. Okay. And then and so you're going to see the same thing about your plus and minus for heat that you're about to see here. If you write this out as 1/2 mv final squared and then a minus sign, and you move this to the other side of the equation, it's going to become a positive, and that's what we have here. We have a positive on this side and also a positive on that side. Okay? But they came from an integral, okay? And the limits would be, one would be a plus and one would be a minus. Now, I only showed you that one. I know that wasn't your question. I show you that one because the same thing happens for heat. When you look at this side of the equation, if you use the force of gravity, you would get these terms. If you use the force from a spring, you would get the 1/2 kx squared, which I didn't include. And the one you're asking about is if you use the force of friction, what you would get is, because of the dot product, you would get a negative. Then you would have the force of friction times the distance it moved. And then if you take this with a negative and move it to the other side of the equation, you would give it a positive and call it heat. So on Doug's equation, he's leaving it on this side and calling it work done by a non-conservative force.
Okay.
But if you look at how to calculate that, you will see a negative force times distance, frictional force times distance.
Okay.
And then on my side of the equation, I will put a plus sign because I've moved it over. That's why that's negative on this side of the equation, but positive on the other side. But it's still going to be frictional force times distance.
Gotcha. Okay, cool.
So it really kind of depends on how you want to view it. If you leave it on the left-hand side of the equation, you view it more this way. You say this is the initial energy minus what is lost by non-conservative forces equals your total energy.
Mm-hmm.
If you put it on this side of the equation, like I kind of like it, then you're saying your initial energy then becomes final energy, including heat as one of your final energies.
Okay, cool. I think that clears it up. Thank you.
So it's just a matter of how you want to look at it. And then, well, of course, like any math, what side of the equation you put it on changes it from a plus to a minus.
Mm-hmm.
All right, so that was actually a really good conceptual and even mathematical, but a fundamental question. All right, so now back to the specific problem. All right, so I'll kind of rewrite that equation. Mm-hmm. So I have this. I have the mgy initial and the 1/2 mv initial squared equals mgy final plus 1/2 mv final squared plus any heat if there's any friction. And I thought I remember reading, I didn't write it down in my little picture here, but there, I believe it said no friction, right?
Yeah, it does.
Okay. So I'm glad I brought up friction because it hopefully gave you some insight to that question. But the truth is, because, and I'll go back to our little calculation, because the frictional force is 0, this calculation for heat is going to be 0.
Gotcha.
And so I'll just cross it out. And I was tempted when I first started writing it, not even to write heat because it was 0, but I thought maybe, and I'm glad I did now, this might get into a deeper conversation and enlighten you a little more. But it's also the same reason why I did not include the 1/2 kx squared, because there's no springs involved in here.
Yeah, that makes sense.
And so, yeah, and I'm not even going to write it because I don't think that leads to a deeper conversation in any way for this problem. Okay, so if we now put in the numbers that we know for this problem, we've got the mass at 120, G is 9.8. The vertical height it starts with, I wrote down as 23.6. And maybe just to make it look complete, I'm going to put down a 0 for the initial speed. So that's an important first step. Then it goes down to the bottom and around the loop. And so down to the bottom and around the loop is kind of this mental picture I have in my head here. And so now it has a height that is the diameter of this loop. And coming back to what I wrote down, it looks like 6.86 is your radius. So let me double that. What does that become? Well, that's a 12, carry a 1.
13.72?
Yeah. Okay.
I'm trying in my head, but I'll use a calculator.
Yeah, it was.
Hey, I nailed it.
Good. Good. All right, so 13.72, and then you have the mass again in the kinetic energy, so 1/2 120, and then final speed squared. Okay, so with what I've done so far, I could actually then calculate its speed there. All right, so I'm going to give it a shot here. So 120 times 9.8 times 23.6 is this side of the equation.
All the masses would cancel in this, would they not?
Good point. We could do it that way also. Yeah, and save a couple buttons on the calculator. But since I'm this far along, forgive me, I'll keep going. Take that number and minus 120 times 9.8 times 13.72. I did something terribly wrong. I got a negative number. Let me go re-enter. What the heck did I type in wrong? 129.8. No, I'm gonna try this again. 120, 9.8, 23.6. I don't think that's the answer I had before, so I think I made a mistake back at that one. Okay, then minus 120 times 9.8 times 13.72. All right, and I'll just do this as an intermediate step, but it looks like I have 11,619 joules is equal to this 1/2 times 120 times final speed squared. That's a 60. So if I just go divide by 60 and then take the square root, I get a final speed of 13.9 meters per second. Fair enough?
Yeah, for some reason I got 14.27, but I may have done something wrong there too.
Yeah.
120.
Maybe I'll try it your way. I'll cancel off the mass.
I actually do.
9.8, 23.6 minus 9.8 times 13.72. Then it would be times a 2 and then a square root.
No, it looks like you did it right and I messed it up somewhere along the lines.
Now, I got that number twice, although I could have made the same mistake twice. That's common.
Yeah.
So
the number is less important than the process.
Yeah. Okay. And I guess you could shoot it into the computer there and see if that tells you. Oh, but that's not what we're.
That's not our
the final
answer.
part. Yeah. Okay. So now the second half of this is, I think, really your main question. The second half of this, then, and I'll draw a free body diagram, and maybe I'll just kind of make the roller coaster kind of upside down here, and so maybe here's the track of the roller coaster as it goes around. But a free body diagram would look like this. You would be pushed down because of the force of gravity, mg.
Mm-hmm.
And then you would be pushed, and this is kind of interesting here.
Down by the normal force too.
Yeah, and this is kind of my issue a little bit with the word roller coaster, because roller coasters, the wheels are locked around the track, and the track can actually push up as well as down. But let's just take it as a car. A car on a road, the road can only push one direction.
Mm-hmm.
And so if you drive a car on a loop that's upside down, the road can only push down.
Gotcha.
It doesn't have these fancy wheel sets that can actually lift up when it's upside down like that. But for safety reasons, you want it that it can't fall off the track if something goes wrong. So when you see these roller coasters stuck in the upside down position, they don't fall. They're
Totally.
Anyways, so I think implied in this problem is that it's more like a car, a stunt driver going around a loop where the normal force can only go down.
Okay.
Okay. So now this is the part that takes us back to Newton's laws. And so remember, the sum of all the forces have to equal ma. And here's where the math starts to come into play. And I guess I'd have to ask you, when I do a grid here, so I'll do kind of a traditional grid, clearly the forces are down. Do you want to call that, and it's a two-part question, do you want to call that the x-axis or the y-axis? And do you want to call down positive or negative?
To me, I usually do better with just calling down negative, but I mean, to me, I don't see a huge advantage to calling it X as opposed to Y, and I don't see a huge advantage as to calling it positive or negative. I mean, do you see an advantage to be gained by messing with it? And this one, I don't particularly see it.
Good. No, I don't, and it wasn't so much about an advantage. It was more of getting you to respond to that question that, hey, I should probably ask myself, is there an advantage to making a different grid? And you answered it well, so good.
Okay, cool.
Okay, so I'll just go to the traditional one. I'll call it the y-axis, and I'll call down negative. And so, of course, what that means is my two forces are negative. So the normal force would be a negative, and mg would be a negative. It also, though, and here might be the part you're struggling with, if you go in a circle, what is the acceleration?
It's, it's the centripetal acceleration, and it's going to be v squared over r. That's what we're looking for.
Right. Okay. And what direction?
It's going to be out. Right? Pointing out of the circle, like parallel to the tangential acceleration?
No. You have to pull something in. Think of a baseball on the end of a rope, and you're standing there spinning it. Which way do you pull on the rope?
Oh, right. It's going in. Okay.
Now, good, and I'm glad I asked that, because it's very easy to say outward, because that's kind of what it feels like if you're in the baseball, if you're in the car. Okay, but that's not the right perspective. The car tires, if you're turning on the road, the car tires are pointing inward towards the center of the circle.
Okay.
Now, so the two parts of this is, what's the magnitude, v squared over r? The other part of this, though, is what direction is it? And it's towards the center of the circle. And if you come back to our diagram, the center of the circle is in the negative direction. So I need to put a negative there. The only small advantage I saw earlier when I asked you about what grid to use, if you had called down positive,
then we wouldn't have all these negative signs.
Yeah.
Okay.
And it's easy to make a mistake right here and forget this negative. It's towards the center of the circle. But of course, now mathematically, if you just multiplied everything by -1, you get a plus n, a plus mg, and a plus mv squared over r. So you would get exactly the same thing as you call down positive.
Okay.
So, like you said, I didn't see an overwhelmingly reason to call down positive, but there was a minor one, and that would be it. You could just kind of skip all those negatives. All right, so now we can get to this question, which is going to say then it's mv squared over r minus mg. And if I go to put in my numbers, then maybe I'll do that on another piece of paper. I'm now going to have the normal force here. And so here's the 120. Now you see why it was important that we did the energy calculation to figure out how fast it was going. That's where that 13.9 is going to come from.
Yeah. Okay.
Although I suppose if I had done this step first, you would have got here and then stopped and said, oh, I have to do energy. So maybe I should have done this step first and go, oh, this is why I have to do energy.
Yeah.
Because you know, when I did it, you didn't really realize why you needed it, but you need it.
Once I saw that we were solving for V, it sort of made it click where we were going to go, but.
Okay.
So I have a question here, which is, what's holding this? It seems to me like right now we've got 3 forces that are pulling the thing off the track.
Oh, careful. No. There's, I'm glad you said that. There's 2 forces. It's just the normal and gravity. The third force is the net force. The third force is the result of those 2.
Okay.
So the mv squared over r is not a force pulling it down. It is, the centripetal force is the result of 2 other forces. So centripetal force is, just the word I think is a little misleading. It makes you think there's a third force. There's not a third force. There's 2 forces. The result of those 2 is the net force.
Okay. Gotcha.
I don't know if this is a silly example, but if you and your friend, you have $10 and your friend has $20, together you have $30. You don't have 3 friends where you have 10, your friend has 20, and your third friend has 30. Those are not 3 pots of money.
Okay.
They're 2 pots of money. It's you and your friend, and then it's the total of you and your friend.
Okay. Okay.
Now, let me also expand. I kind of got the impression from your question that you were saying, well, what's holding it up then?
Yeah.
And it's not so much what is holding it up as, let's see if this picture helps. If you had a roller coaster without a track, but somehow it got upside down and was moving at 13.9 meters per second, gravity would pull it down in the shape of a parabola. So if your track curves more than it would have gone because of the force of gravity, then you're essentially saying it's stuck to the track. Not that there's a force sticking it, it's that you might say the track is kind of getting in the way.
Okay.
And then, of course, the reason it turns and stays on the track is because there's an additional force, which we call the normal force, pushing on it. Gravity by itself would only make it go in a parabola.
So the normal force of the track is what's turning it. Okay.
Yeah, it's what's turning it. And it's not making it stay on either. It's that the track's kind of getting in the way of its natural direction it would go with just gravity alone.
Okay. Cool.
And so that's why if you made a track that looked like this, if the track had less of a curve to it, this thing would fall off the track. Because this is what it would do with just gravity alone.
Okay.
And the track doesn't really get in its way. And that's what they're leading up to in the next question, or the part B of this question.
Got it.
So I'm going to get a number here, and then we'll go on to your part B. So 120 times 13.9 squared divided by 6.86. It's kind of that first number. Then minus 120 times 9.8 comes up with a normal force of 2,204 newtons. So this is the normal force at the top.
Okay.
And so they're, they answer, so the roller coaster is actually pushing down. That's why I'm going to assume you've been on a roller coaster and gone upside down on these.
I have been on a roller coaster upside down and not upside down.
Okay, and when you're upside down, you actually feel the seat pushing on you. If you were to close your eyes, you might not even know you're upside down.
Yeah, that's true.
So it's and it's actually kind of a safe way of making a roller coaster, because if something goes wrong, you're kind of stuck to it. That's why those stunt riders and those cars and those motorcycles can go around the loop that way.
Mm-hmm.
It's got to be going fast enough. In fact, one of my favorite ones is the two motorcycle riders and the ball of death. It's a little tiny ball, and you got two motorcycles. It's crazy.
Yeah.
You got to go so fast or you're going to fall.
You put two of them in one of those things?
Yeah, it's a little ball. It's like this.
Yeah, that sounds crazy.
You got one motorcycle going around this way and the other one going, around this way, but timed so that when one's at the top, the other one's at the bottom. And so you got to go fast, and you got two of them that cross paths, and it's
yeah, that's
definitely the ball of death.
Yeah, that's not what that sounds like a little more than I'm trying to sign up for.
So, okay, so continuing on here.
That answer is right, by the way. So whatever, I just checked it. So that's the right answer for N top.
Oh, good. Yeah, and I know that anybody who watches the video later knows the numbers will be different, right?
They're slightly different, but they're usually like ballpark similar, so.
Okay. Yeah, well, that's why I like to put the symbols here for anybody who's watching it later. They can put their numbers in. Okay, so then the other half of this, and then now you're, I think, kind of got the clue of this, and that if you don't start with the roller coaster at a high enough height, then as it goes around, it will, instead of follow the track, it will do something like this. It'll fall off. It'll be kind of like I was saying back here, where what's keeping the roller coaster on, there really isn't a force. It is really and I'll say it's the momentum or the velocity of it, but that's not really what's keeping it on. What's keeping it on is not a force. It wants to follow a path of this parabola, but if the track turns at a greater rate because of its speed, it will essentially be crashing in to the track, and that's what kind of holds it on. It's speed, it's momentum. So if the roller coaster is going too slow, and so if here's the loop, and up here at the top, if it's going too slow, if its natural path is a parabola that looks like that,
yeah,
well, then it's not going to stay up there. Okay, Except, as I said, roller coasters don't do that because they're really designed to be, you know, hang upside down if they weren't even moving.
Yeah.
So, but let's say it's more of a stunt car.
Motorcycle on a stunt loop.
And a motorcycle. Yeah, if these stunt guys aren't going fast enough, they're going to fall off. All right, and so we can figure that out back in this equation. From back here, we had this equation earlier in part A, I'll call it, where this is the normal force. And in fact, if you take a moment to kind of read this equation, you'll give you some insight to this loop, and it'll be saying this, that in order to make the loop, you need this much force, okay? Pulling you downward. Maybe I should put it this way. The two forces together, the normal force and gravity, have to add up to be this amount. So, if your, say this in the right words here, if your speed is so great, like I would say it in this amount, then you need a lot of force to make that turn. You get some of that from the weight of it, and you get the rest of it from the track. And as you go slower, you need less force to make that turn. The weight of your roller coaster doesn't change. And so what that means is the push from the track goes down. And you can see that in this line, right? The normal force is this number minus gravity. So you need, I guess
we're looking for when the normal force becomes zero, right? When the
there
track is no longer happening, then we'll.
Yeah, that's what I'm getting at here, is the normal force will keep going down and down and down and down. And once it gets down to zero, the only way to stay on the track is if the normal force is a negative, if the track can pull you up, which, like I said, in a roller coaster it can, but for a stunt driver it can't. So you can use that argument to say that the slowest speed I could have is when the normal force is zero, which means mv squared over r minus mg has to be zero, which means mg equals to mv squared over r, which means if we cancel the m and put the r to the other side, this would be the equation for the slowest speed. When your speed is that much, your normal force is zero. And anything slower than that requires an upward normal force.
Okay.
Which I'll say it again, roller coasters do that for a safety reason. Something can go wrong. But if everything goes right, they go faster than this minimum speed.
Okay, I'm thinking I'm seeing how this is working out now.
Okay, so if I grab my calculator and go back to the picture of that radius, what was it, 6.86, 9.8, and then take the square root of that, we're looking at about 8.20 meters per second, for your numbers anyways.
Yep.
As the slowest we can go. And at that point, the effect of gravity is just the right amount to give us the centripetal force that we need in order to make that turn. So we don't need any help from the track. Slower than that, we would turn more than the radius of the loop and we'd fall off.
Gotcha. So I think I see where we go from here now. We'll then take that velocity we just found and plug it in for our V final in the energy equation and use that to solve for Y initial? Okay.
And so I'm going to go and put in the conservation of energy that you just said. I'm going to put an equation of the words, because this side of the equation would be this 120 times 9.8, and the height was that 13.72, and now we've got the velocity minimum that we've discovered. And a big part of this problem is to realize that there does have to be a speed at the top of that loop. Sometimes a beginning student will just say, well, it just has to get there, so I can set the speed equal to 0 at the top of the loop, but it'll fall off.
Okay.
And so that's, I would say, the common mistake is to set the velocity equal to 0 at the top. And that's why we needed to go through that discussion. 129.8, and then the initial height. And then I'll take advantage of your point you made earlier that the masses can cancel off. So this would be 9.8 times 13.72 plus 1/2, 8.2 squared, and that would be the right-hand side. And if I divide that by 9.8, looks like a height of 17.2 meters. We just make it. And so our original 23.6 was more than high enough, as we already calculated. It was going pretty good by the time it got to the top.
Awesome.
By the way, if you were interested in a little fun engineering and history,
I am.
This roller coaster idea was proposed many, many years ago, long before they built their first one. The first loop like that was in 1976. If you ever go to Magic Mountain, it's the old Revolution.
Really?
And, yeah. And that
they
was
got rid of the Revolution. Sadly, it's a new Revolution, I believe now.
Oh no!
The OG is gone.
Wow.
Yeah, it still has the same name, but they replaced it with steel and made it a different roller coaster, I think.
Yeah, I gotta admit, it's not the best roller coaster by today's standards, but I remember when it opened in 1976. I was
That was
10
the
years
first
old.
ever loop, huh?
I was a 10-year-old boy, and it was like, oh, they finally built it, because the people I talked about it. But here's the interesting engineering I wanted to point out was that when you run through these numbers, to go in a circular loop like this, there is so much G-force on you at the bottom in order to make sure you don't fall out at the top, that it was considered an impossible ride to make or to do. And so I was going to say, if you've ever been on the bottom of this, when you come out of this loop down here at the bottom, you're really shoved down.
Yeah.
Because you're going so fast, and there used to be a little sign, a little trick here, that when you go up at the top, you're supposed to lean your head back and keep it in that position, so that when you come around to the bottom, the force kind of throws you down this way. If your head was down, when you get down to the bottom, you go
face first.
you get shoved down. Yeah. So they didn't think humans could really handle it, but Magic Mountain built it anyways, and that was their claim to fame. And this great roller coaster was, I think they're only their second roller coaster, because the Gold Rush was the first one. And well, there were wood roller coasters, but I don't think at Magic Mountain. Anyways, all that is to say, then the design was, somebody came up with what now you see today is the teardrop. You do this. Maybe that's a little exaggerated. But the top of the loop has more of a curve than the bottom and the edges.
That makes sense.
So you don't have to go nearly as fast. And so somebody very cleverly came up with that design. And then even then it was many, many years, I think even decades before they could actually build it, because they didn't have any manufacturing equipment that could build metal tubing of the appropriate shape. They could only do the circle.
Huh.
And then of course, once they got to the teardrop, now today it's not a big deal to go over a loop. You don't.
Yeah, I feel like if you could also find a way to, instead of when you're coming out of the loop, to just go back to something horizontal, if you could come out sort of at an angle that continued down a little bit, then they could slow the sort of.
Yeah, I wondered if they should do, some kind of a loop, and then as you come out, you do a twist.
That's.
You do a loop and then followed by a twist.
I think Magic Mountain's one of their newer roller coasters actually does that.
Yeah. Okay. And it's been years since I've been to Magic Mountain.
Me too.
Grown up, and my kids have grown up. I don't make it there now anymore. Once they got to be teenagers, they wanted to go without me. Go figure. So. What else? Oh, I was going to throw in this. And so, by the way, in a little fun history there too, is then Knott's Berry Farm responded with their corkscrew ride.
Mm-hmm.
And that was also considered one that would be too hard on a human. But what they did, if you look at the corkscrew at Knott's Berry Farm, they made it so that the track makes a kind of a corkscrew. There's two on the original one anyways, but the head of the human is near the center, and really the human barely goes around any circle. And so you just kind of do a pivot, the track goes around and you just kind of pivot, and your head really doesn't go into a circle much, and so there's very little force on the human.
Interesting.
And it's more
the
of
human went through a bigger circle. Would they pass out because there'd be too much force?
I don't know how much force there would be. Yeah, but I don't know if they would pass out. I think some of these roller coasters these days have gotten much more extreme, but there was a time where the design was not to make a human on a roller coaster go above 2.5 Gs. But I think that has changed. I think now they're 3.5 Gs are some of these rides. I'm not real sure on that number. I think, what's the other one, the Goliath, where at the end of Goliath, you go through a series of horizontal loops. I think there's 2 of them, and you make kind of a tight turn. And I think that's a 3G turn. And that's kind of considered the edge. I mean, if you're young and healthy and a teenager, you don't think much about 3Gs. You're old and don't have as much blood pressure.
What do they put these like astronauts and like fighter pilots up to these days?
9 Gs.
That's a lot.
Well, the fighter pilots go 9 Gs. Yeah, very much. The astronauts, I don't know if they go that high anymore with them. They used to give them to 9 Gs, but even most of our rockets, and particularly the space shuttle, well, they called it a 3G machine, because if it ever accelerated more than 3 Gs, it would tear itself apart.
Huh.
So, yeah, but an F-22 or an F-16 can hit 9 Gs.
Wow.
And humans, if you're in good shape and trained and have one of those pressurized suits, you can do a 9G. Yeah.
Wow. Cool. Well, thanks for spending so much time with me going through that problem. I feel like I understand it way better now.
Oh, Cool. Yeah, I got lost on roller coasters. Okay, so.
No, you're good. I'm sure someone else has
Let's
question.
see. I should move on. Okay. Let me go to the chat here. Scott, you came in here with 29. All right. Number.
I think Danny came in after Rylan and has a question before me.
Oh, you want me? Okay. All right.
I don't want to skip Danny.
Yeah. Okay.
You sure, Scott?
Yeah, he already answered one of my questions. I don't think he's answered one of your questions yet.
Okay. Cool.
All right, Dan. So what do you say? Chapter 28, number 54?
Part B. I'm
Part
just
B.
having a hard time understanding what to do in it, kind of.
Okay. Let me look that one up here. So chapter 28, number 54. And let me come over here to the questions. Oh, that's chapter 29. Let me go back. Okay, chapter 28, 54. In figure 59, and I might have to, you said part B, but I might need to, and I'm reading the wrong one. Okay, 54. A young man owns a canister vacuum cleaner marked for 535 watts at 120 volts and a Volkswagen Beetle, which he wishes to clean. Okay. So he parks the car at his apartment building, and uses an inexpensive extension cord that is 15 meters long to plug in the vacuum cleaner. You may assume that the cleaner has a constant resistance. Okay, so let me just do I know that's not your question, so maybe I'll do it kind of quick. If the resistance of each of the two conductors of the extension cord is 0.9 ohms, what is the actual power delivered to the cleaner? Okay, so I'm going to do this, that V squared over R is equal to the power when they rate something. So this is 120 volts. The vacuum cleaner says 535 watts. A little bit of math then tells me what the resistance is in the wirings of the vacuum cleaner, mostly the electric motor. And so if I go
like the load, right? The load of the vacuum.
Yeah, the load, exactly. And so this would be ignoring any resistance from the extension cord. Okay, so just the vacuum cleaner itself and all the parts that go with the vacuum cleaner. So 535 divided by 120, take the reciprocal of that, and it looks like I'm getting a number of about 26.9 ohms for just the resistance itself. Now, if you were to hook it to an extension cord, and in this case, they're saying a cheapy extension cord, so that the 15 meters of wire. Oh no. Wonder why I lost that. Let me try it again. But the 15 meters of wire, if I read this right, each had a resistance of 0.9. So I'm going to put 0.9 ohms here and 0.9 ohms here. And then this little drawing will be the vacuum cleaner itself, which we already said was 26.9 And so with the extension cord, there would be the 26.9 plus a 0.9 plus a 0.9, the two wires leading out. So this is a 28.7 volts. And let me just come to this question. If the resistance of each of the two conductors is 0.9, what is the actual power delivered? Okay, so then when I go V squared over R, which is the 120 squared, I would have to be dividing it by a resistance that's a little bit more, it'd be the 28.7, than what was actually, in the vacuum itself.
Because it's hooked up to the extension cord.
Yeah. Which
Okay.
is why, some devices that are already just barely getting enough power to run will say, do not hook up an extension cord. I know my air compressor is that way. I've got this air compressor and it's got about a 3-foot cord on it. And it says, do not use an extension cord. And of course, when I first got it, I was like, okay, I got to use an extension cord here to see why do they say don't use an extension cord. So I put it on an extension cord, and sure enough, as soon as I turned it on, it wouldn't turn over that compressor motor. It was just like, it was just stuck. So then I disconnected the extension cord, and when you plug it straight into the wall, it goes, the lights dim, it goes, just barely starts. So it's somebody designed this compressor, obviously to be right at the maximum, but not require 240 volts. A lot of compressors run on 240 because they take so much energy. But this was a one, I got it because it was the most powerful one I could find that would still run on your regular 120 volts. But then I ran into this problem that I couldn't run it with an extension cord. But of course, the answer to that is just a long air hose, so I was like, so it's kind of stuck in the back of my garage. But if I, wanted to take the lug nuts off of my car, I just have to have a long air hose. So I kind of glad I have it because I like how much power it can put out, but I'm kind of disappointed because it's stuck there. I can't move it more than 3 foot from an outlet. Otherwise it won't work. Okay, so back to these numbers here. So this would be 120 squared, and then divided by that last answer. And it looks like I'm running this vacuum on a little lower power, 501 watts. But of course, so my vacuum is not as strong as I'd like it to be, or as much as it could be. However, I also, have it maybe out in my driveway and I'm able to clean my car with it. And so better to have it running at 500 watts than nothing at all. Of course, the 535 is what it would be even better.
So is that the total power, the total wattage? Because I got.
Oh, excuse me. Yes. Good point. That is the total. That's including the heat in the extension cord, not the vacuum cleaner.
Okay.
Yeah. So I probably should have done this a different way. You're right. I think I hear where you're going with that. If you went to figure out how much current was flowing,
you could just use voltage times resistance.
Yeah, I was wondering if that's the better way. Yeah, I think that's the better way. So let's take voltage divided by the resistance. So this is the 120 divided by the total resistance of 28.7. 120 divided by 28.7. And so this would be 4.18 amps. And to find out how much is going just to the vacuum cleaner. See, what I did was the total power. But I'll do maybe this I squared R. And so 4.18 squared, and the resistance of just the vacuum cleaner would be the 26.9. And so I will square that and multiply it by 26.9. And so did you get this 470.3 watts? Yeah.
I just got 470. I didn't get the 0.3.
Well, and probably because I didn't really put in 418. I just carried the whole thing and squared it. So forgetting that would be the number there. In fact, maybe I'll check the solution guide here so that I don't mislead you, or maybe you already have.
Yeah, I checked it for part A.
Okay. So 54 says, yeah, the amps 418, power delivered, 470. All right. So we're on the same discussion there. And sorry, I didn't read the question well. This is the power total delivered. And so the heating of the extension cord and the running of the vacuum cleaner is 501. So it looks like there would be 31 watts of heating for the extension cord.
Okay.
So now I can finally really get to your main question, which was B. It says if instead the power is to be at least 525 watts, what must be the diameter of each of the two identical copper conductors in the cord that he needs to buy? And so, if you ever go down to buy extension cords, that's why you have things like, here's a 100-foot extension cord, and it'll say 16 gauge. And there'll be a 14 gauge, and there'll be a 12 gauge. And so the 12 gauge is a bit pricey because it's got thicker diameter copper wire in there. And, and if you want to get that much power, then that's what you got to pay for. You got to pay for more copper. Okay, so coming back to your part B then, and if I go I squared R again, and I want it to be 525, and then this R, and this is the power in the vacuum cleaner. Let me just read that again real carefully. Not the power total, but if instead the power is to be at least 525. And I think they mean in the vacuum cleaner.
Mm-hmm.
So I'm going to put then 26.9 for the resistance in the vacuum cleaner. And then this would tell me.
We're just ignoring the extension cord at this point, right?
I don't want to use the word ignore as much as I said I don't need it for this calculation. It goes through the extension cord. And so if I was drawing a picture, here's the plug, let's say. It would go through the extension cord, then through this vacuum cleaner, and then down the extension cord. So whatever goes through the extension cord goes through the vacuum. And so I'm going to use this to figure out how much current should be in the vacuum, but then I'm going to use that to say how much is actually in the extension cord.
Okay. That makes sense.
So I'm going to go 525 and divide it by the 26.9. And then I'm going to take the square roots and say that in order to get this much power into my vacuum cleaner, I need to make sure that what's running through my circuit is 4.42 amps. And then, kind of like we did in A, but in reverse, if I said that this one wire right here had a resistance of, well, let me not use capital R, that might confuse you. you know, because in part A, they said 0.9. Let me just call it little r for a moment. Because current is voltage divided by the total resistance. And the total resistance would be the resistance in the vacuum cleaner plus 2 little r's. Again, if you let R be the resistance of one wire in your extension cord. So I want this current to be 4.42. I'm going to plug it in to 120 volts. And then I want to solve for how much resistance would be in that one extension cord. So 120 divided by 4.42 gives me about a 27.149. Subtract from that the 26.9. Divide that by 2. And so this would work as long as my extension cord had a resistance of only 1/8 of an ohm, 0.125. Okay. And then going back to chapter 27, I would say that the resistance equals the resistivity times the length of it divided by the cross-sectional area. So the resistance, I want to be this 0.125 ohms. The resistivity of copper. Okay, well, let me switch over to the textbook here. And let's see, I believe that was in chapter 27. Okay, maybe I need to make my screen a little bit bigger so I can see it. Okay, there's table 1. There's table 2. Okay, and so if I look up the resistivity of copper, I've got a 1.7 times 10 to the negative, make that bigger. Why does this thing default to 50%? Yeah, 10 to the minus 8, good. And then the length of it, I believe they said this was a 15-meter long extension cord. It's about 50 feet.
Yeah.
Okay, so that's 15 meters. And then they say, are we looking for diameter or radius here?
Diameter.
What is the diameter? Okay, so, well, I'll write it as radius for just a second and then eventually get diameter. All right, so using the come back here to the Zoom here. There we go. Okay, then this would be, so I've got the 1/4. Why don't I do this? I'll just write it as r squared equals 1.17 times 10 to the negative 8 times the 50.
I think your screen is frozen.
Divided by, pi. You're right. Let me come back here. Why does it say my screen? Oh, you know what? When I went to the textbook, it froze it, didn't it? Okay, so how do I get back? Be nice.
I think the break time is coming up, right?
Oh, I don't know. I've been looking at the clock. Oh, yeah, I guess so. But wait. Hey.
Well, I'm going to go get some food and take a small break, and then I'll come back later for the next session, and I'll bother you with my questions.
Okay, okay. Please do, but I'm getting annoyed with my Zoom here. How come I can't get back to where it says share?
I'll be back. Thanks.
Okay. It says
Good
these are
job.
the controls. That's good. New.
Maybe reload your phone.
Yeah, I'm gonna do that. I don't know what.
It's not sharing the phone anymore, so your screen's not frozen on that anymore.
Okay.
So
All right. And I don't know what exactly completely happened. I know it stopped sharing. I thought that was just the problem. Once I switched over to the textbook, I kind of get that. I should have done it on my other computer. But let me reinitiate it again. Okay, so this is the part I wrote before I lost you here. But so let me just kind of recap. So this is the resistance I want. This is the resistivity I just looked up in the textbook. This is the 15 amps. And if I put all these numbers, then it's not sharing anymore.
Oh, okay, I see.
Yeah, it froze again.
So then I would just, so that's the area of the circle is pi r squared. So then I would just solve r squared and then double it.
Exactly.
Okay.
Exactly.
Okay, I think I can figure it out from there.
Pick it up here. I'm gonna try to connect again.
I was confused by the solution because at one point near the end they just kind of put a 4 in there, and it didn't make any sense where that 4 came from. Like I didn't.
So they did this, I bet. Right here at the radius, you could say the radius is the diameter cut in half squared.
Uh-huh.
And so that right there would be diameter squared over 4.
And since the area is on the bottom, it put the 4 on top.
Yeah.
Okay. Yeah, I was really confused by that, but I like the way you did it better. It makes more sense.
Yeah, sometimes it just is a lot better to make little calculations instead of trying to do everything in one shot. So it's kind of easy to just get radius first and then double it.
I was able to find a I totally forgot about this website, but I was able to find a website that has like people who work the problems through, and sometimes because these solutions sometimes are just the answer and doesn't really explain where something came from.
I totally agree. I think the author. I'm just checking the answer. Okay, good. 1.6 millimeters. Yeah, the one question that Scott asked at the beginning. They just threw out this equation that had a t in there, and he assumed it was time, and I did too, and we had to work all the way through, and eventually figured out that the t was for thickness, and that equation was never in the book. So the people doing the solutions aren't really taking gentle steps, if you will. They should start with an equation that's in the book that they already know about and then work from there, but they don't at times.
Yeah.
Yeah.
And so every once in a while I've been just using this website where it's like a bunch of different science and math books, like it has the homework for them, and it's done by students, and they explain like how they get some stuff. So it's like, but they don't always have help, and this was one of the problems that they didn't have help on. So I was like, but it's actually been helping me a lot, because sometimes when I don't understand a solution, I look at that website, and then it has a more clear version of that solution, and
that's good.
Yeah,
that's real good. That's kind of what this whole new learning world is by remote. That is so different. It's new to everybody, and we're all trying to figure out what's the most successful way of learning in this
it's
weird environment.
it's definitely tough, that's for sure.
All right. Well, why don't we take our break, and we'll come back and at 12:30.
12:30, right?
Yeah, I think
Okay.
those are the times. Yeah, come back at 12:30 and keep going along. All right.
Cool. See you in a little bit.
All right.